In the cold silence of the universe, far beyond the reach of human hands, two titans drift through the void. They are not alive in any conventional sense. They do not breathe, they do not think, and yet they dominate everything around them. Born from the cataclysms of dying stars, they are relics of death and engines of cosmic power. One is a collapsed core of pure nuclear matter, a sphere so dense it defies imagination. The other is an invisible abyss, a region where space and time fold into nothingness. These are the Neutron Star and the black hole, two of the most extreme objects the universe has ever known. And today, we bring them face to face in a cosmic duel that transcends anything seen on Earth. A neutron star is the corpse of a once massive star left behind after a supernova explosion. What remains is a ball of pure neutrons, compressed into a volume just a few kilometers wide, but with more mass than the entire sun. To imagine its density, consider this. A single teaspoon of neutron star material would weigh about 1 billion tons. Its gravity is so intense that anything falling from just a meter above would strike the surface with the energy of a nuclear bomb. These stars often spin with terrifying speeds, sometimes hundreds of times per second, producing pulses of radiation that sweep across space like lighthouse beams. Some of them, known as magnetars, possess magnetic fields so powerful they can tear apart atoms from vast distances. Yet even these monsters pale next to a black hole. A black hole is not an object in the traditional sense it is, a region of space where gravity is so strong that not even light can escape. At its core lies the singularity, a point where all known laws of physics break down. Surrounding it is the event horizon, the point of no return. Anything that crosses this invisible boundary vanishes from the universe as we know it. Black holes are born when stars even more massive than those that create neutron stars collapse under their own gravity. Unlike neutron stars, black holes have no surface, no features, no light. They can only be detected by how they interact with their surroundings by warping space, pulling in matter, and sometimes by unleashing jets of energy so powerful they outshine entire galaxies. To compare these two is to pit two extremes of nature against each other. The neutron star is the limit of matter, the final stand of particles against collapse. The black hole is the surrender, the collapse itself, a place where the universe ceases to function in any recognizable way. The neutron star holds its shape through a delicate balance of quantum forces and gravity. The black hole has no shape, no surface, just a gravitational trap deeper than anything else in existence. If the neutron star is a fortress, the black hole is a bottomless pit. Consider gravity, the force that defines both of them. On a neutron star, gravity is so strong that the curvature of space becomes extreme. But it still obeys physics. The black hole doesn't just bend space, it shreds it. Near the event horizon, time itself slows down. From a distance, an object falling in would seem to freeze in place. Inside the event horizon, time and space switch roles. Movement becomes meaningless. The singularity, the center of the black hole, is a point where density becomes infinite. And even the best equations in physics collapse under their own weight. Now, consider magnetism. The neutron star may well be the most magnetic object in the universe, especially in the case of its magnetic fields are so powerful they could destroy electronics or kill a human from 1,000 kilometers away. They are capable of twisting atoms into thread-like shapes and releasing flares of gamma radiation that can travel across galaxies. Black holes don't possess inherent magnetic fields because they have no surface. But when they consume matter, gas, dust, or stars, they can generate swirling disks of plasma. From these disks, magnetic forces can arise, fueling colossal jets that launch material at nearly the speed of light. Though the black hole's magnetism is borrowed, its effects are devastating. When it comes to rotation, both objects spin at terrifying speeds. Some neutron stars rotate faster than kitchen blenders, hundreds of revolutions per second. These pulsars beam radiation with such regularity that we use them as cosmic timekeepers. But black holes to spin. Some rotate so quickly that their event horizons are nearly flattened. Their rotation drags space-time itself. Along with it, the phenomenon called frame drag. Any object nearby is pulled into this twisted swirl of warped space. And the faster the spin, the more powerful the effects. In this arena, the black hole doesn't just rotate, it changes the very nature of motion. Despite all its strength, the neutron star is fragile in one important way. If it accumulates too much mass, say by pulling material from a companion star, it can collapse under its own weight. And when that happens, it becomes a black hole. It is the ultimate surrender. The neutron star has a limit. The black hole does not. There's no known mass threshold where a black hole will collapse into something else. In theory, they can grow forever by eating stars, gas clouds, other black holes, or even neutron stars. Their stability is terrifying. They don't decay, don't weaken. They persist, silently shaping the universe. When these two titans meet, there is no tie. The neutron star is torn apart and devoured. The collision sends out gravitational waves ripples in space-time that travel across the cosmos. We've detected these waves here on Earth using observatories like LIGO and When we do, we are literally feeling the tremors of distant cosmic violence. Sometimes, before being consumed, a neutron star is shredded into glowing arcs of matter. Other times, it disappears without a trace. In either case, the black hole grows larger, more massive, more powerful. And yet, for all its dominance, the black hole remains a mystery. We understand neutron stars, at least partially. Their structures can be modeled, their emissions studied. We can chart their behavior and simulate their collisions, but the black hole defies understanding. What happens at the singularity? Is information truly lost? Are black holes portals, as some theories suggest, to other universes or different dimensions? Are they one-way tickets to oblivion or something far stranger? These are questions physics cannot yet answer. They sit at the frontier of knowledge, daring us to discover more. So who wins this cosmic duel? In terms of raw power, the black hole triumphs. Its gravity is unbreakable. Its presence erases all opposition. But the neutron star leaves behind more than just its crushed core. It leaves insight, challenge, and hope. It shows us the resilience of matter, the extremes of magnetism and density, and the strange elegance of quantum forces balancing against collapse. It is the last stand of a dying star, and in its flickering pulses, it tells a story the black hole never will. Perhaps that's the real difference. The black hole devours and silences. The neutron star shines and speaks. Even in death, it communicates. Across light years, across time itself, its signals race through the darkness. And somewhere in the black night of the universe, a neutron star spins in orbit around a black hole, drawing ever closer to its end. With every turn, it sends out gravitational whispers and pulses of radiation. We listen. We learn. And in that final spiral, just before annihilation, the neutron star may give us one last clue about the nature of reality. In this cosmic clash, it's not about trophies or victory laps. It's about understanding the forces that shape everything from galaxies to atoms. It's about witnessing the fury of collapsed stars, and through that fury, catching glimpses of truth. Indeed, that conversation is just beginning.